From this short video, I want to discuss or basically to introduce you the idea of electric potential. Before I discuss electric potential, let me go back and discuss about electric field a little bit, because that you are very familiar with electric field now. And if I remind you that how we define electric field, so I'm going to assume some source charges. So let's say that I have few source charges which are positive and they are located like that, okay? And as a result of these few positive charges, and we know that everywhere around it, so there is an electric field. So the strength of the electric field varies with the distance, and the symmetry of the charge distribution basically reflects the symmetry of the electric field as all of those facts. And if I want to measure the electric field due to these source charges at some point in space, let's say I want to figure out the electric field at this point, what I would do is that I would bring a test charge, and which has to be positive. So if you bring a positive test charge Q and place it here and measure the electric force on it and divide the electric force by the charge you brought in, and then you find the electric field. So that's how we calculated electric field, and that's how we define electric field. If I write that, so it is E at, let's say this point is A. E at A can be written as F E at A divided by Q. And you know that the direction of the electric force is going to be the direction of the electric field as well. And that is the definition of the electric field. And now the electric field was defined with respect to the electric force. And not just the force, we talked about electric potential energy, so which is the interaction energy of the system. Yeah. So can we define some quantity like electric field for electric potential energy as well? So if you think a little bit further about it, so of course that you can define something similar for electric potential energy. Okay, so let me go to this side now. So now look at the system in terms of energy. Okay, so when we think about the energy of the system, so we are talking about electric potential energy of the system. Okay, so if I think about the same charge Q that I brought in previously, so and I'm thinking about the same point A. Okay, so we have the same point A and I'm bringing the same charge Q. In order to bring that charge Q to this point A, I have to do some work on the system. Okay, so that interaction energy is stored in the system as the electric potential energy, and the electric potential energy of the Q plus source charges system can be calculated. We know how to calculate that. And let's say that we calculated it, and the energy of the system depends on where you bring this charge Q. If you bring this charge Q so close to the charge distribution, so you have to do some more work on the system, and as a result of that, so the whole system is going to have more electric potential energy. Okay, so if you calculate that electric potential energy per unit charge, that means that if you simply divide the electric potential energy that you calculated by the charge you brought in, so you get the amount of work done or the amount of potential energy per unit charge. Okay, if you know the amount of potential energy per unit charge, so then you can immediately find out the total potential energy of the system plus that charge Q just by multiplying it with the charge Q. Okay, so this quantity, the potential energy divided by the charge, or the potential energy per unit charge, is called the electric potential. So look at the similarity between these two. And the electric force was used to define the electric field here. And here we define electric potential using electric potential energy. Electric potential energy is not a vector quantity, and it is a scalar. Okay, so we get the electric potential as a scalar as well. And electric potential energy can either be positive or negative. And as a result of that, electric potential can also be positive or negative. And we know that if the electric potential energy is positive, that generally means that the system has repulsive interaction. Okay, if the electric potential energy is negative, that generally means that the system has attractive interaction. Okay, so now we have the idea of electric potential. Now let's see what the units are. So the electric field, it was simply newtons per coulomb, and the same way for the potential V, so we get the unit joules divided by coulomb. But the joules divided by coulomb is given a special name, volt. Right? It is volt, and we use the capital letter V to represent. And you got to be careful. Now the letter V, the capital V, is used to represent potential, electric potential. At the same time, we use the capital V to represent the unit of electric potential, which is volt. Okay, joules per coulomb, 1 joule per coulomb is equal to 1 volt. So there is a very important thing to note here at the end, that both the electric field and the electric potential are the properties of source charges. For a given point in space, we can define both the electric field and the electric potential. And once we know the electric field, we can immediately find out the electric force on a charge at that point. And once we know the electric potential at that point, so we can immediately figure out the total potential energy of the system when there is a charge at that point. Okay, you simply multiply the charge Q by the electric potential at that point in order to get the total electric potential energy. The next step is to find out electric potential for a given charge distribution.